So a lot of this is a combination of what we've been doing the last 3 classes and adding something a little bit new. And since a lot of it's review, and this is a really long lesson, I'm going to go rather quickly through these, just so the information's there, but a lot of it you already know how to do. It's just adding this little bit in. So the learning target for today is to be able to compute confidence intervals for mu sub 1 minus mu sub 2 and p sub 1 minus p sub 2. For the scale, you're 3 if you can compute confidence intervals for mu sub 1 minus mu sub 2 and p sub 1 minus p sub 2. 2, you can compute confidence intervals for mu sub 1 minus mu sub 2 or p sub 1 minus p sub 2. You're 1 if you can compute confidence intervals for mu sub 1 minus mu sub 2 when sigma sub 1 and sigma sub 2 are known. And you're 0 if you cannot compute confidence intervals for mu sub 1 minus mu sub 2 when sigma sub 1 and sigma sub 2 are known. Section 7.4, estimating mu sub 1 minus mu sub 2 and p sub 1 minus p sub 2. Focus points: to distinguish between independent and dependent samples, to compute confidence intervals for mu sub 1 minus mu sub 2 when sigma sub 1 and sigma sub 2 are known, compute confidence intervals for mu sub 1 minus mu sub 2 when sigma sub 1 and sigma sub 2 are unknown, compute confidence intervals for p sub 1 minus p sub 2 using the normal approximation, and interpret the meaning and implications of an all positive, all negative, or mixed confidence interval. Independent samples and dependent samples. How can we tell if two populations are different? One way is to compare the difference in population means or the difference in population proportions. In this section, we will use samples from two populations to create confidence intervals for the difference between population parameters. To make a statistical estimate about the difference between two population parameters, we need to have a sample from each population. Samples may be independent or dependent according to how they are selected. Two samples are independent if sample data drawn from one population are completely unrelated to the selection of sample data from the other population. Two samples are dependent if each data value in one sample can be paired with a corresponding data value in the other sample. Dependent samples and data pairs occur very naturally in before and after situations in which the same object or item is measured twice. In this section, we will confine our interest to independent samples. Independent samples occur very naturally when we draw from two random samples, one from the first population and one from the second population. Because both samples are random samples, there is no pairing of measurements between the two populations. All the examples of this section will involve independent random samples. Confidence intervals for mu sub 1 minus mu sub 2 and sigma sub 1 confidence intervals for mu sub 1 minus mu sub 2 when sigma sub 1 and sigma sub 2 are known. In this section, we will use probability distributions that arise from a difference of means or proportions. How do we obtain such distributions? Suppose we have two statistical variables, et sub 1 and et sub 2, each with its own distribution. We take independent random samples from size n sub 1 from the et sub 1 distribution and of size n sub 2 and the et sub 2 distribution. Then we compute the respective means, et sub 1 bar and et sub 2 bar. Now consider the difference, et sub 1 bar minus et sub 2 bar. This expression represents a difference of means. If we repeat the sampling process over and over, we will create lots of et sub 1 bar and et sub 2 bar values. So here's just an illustration of the sampling distribution. So we take a sample from population 1, take a sample from population 2, and get averages from them, from those samples, and then subtract them to find the difference. The values of et sub 1 bar minus et sub 2 bar that come from repeated independent sampling from populations 1 and 2 can be arranged in a relative frequency table and a relative frequency histogram. This would give us an experimental idea of the theoretical probability distribution of et sub 1 bar minus et sub 2 bar. Fortunately, it is not necessary to carry out this lengthy process for each example. The results have been worked out mathematically. The Nets theorem presents the main results. So here's the procedure. How to find a confidence interval for mu sub 1 minus mu sub 2 when both sigma sub 1 and sigma sub 2 are known. So requirements. Let sigma sub 1 and sigma sub 2 be the population standard deviations of populations 1 and 2. Obtain two independent random samples from populations 1 and 2, where et sub 1 bar and sigma sub 2 bar are sample means from populations 1 and 2. N sub 1 and n sub 2 are sample sizes from populations 1 and 2. If you can assume that both population distributions 1 and 2 are normal, any sample sizes n sub 1 and n sub 2 will work. If you cannot assume this, then use sample sizes n sub 1 greater than or equal to 30 and n sub 2 greater than or equal to 30. So confidence interval for mu sub 1 minus mu sub 2 is et bar sub 1 minus et bar sub 2 minus mu is less than mu sub 1 minus mu sub 2 is less than et bar sub 1 minus et bar sub 2 plus e. So same thing we've been dealing with, but instead of just et bars, we need to find the difference between the two. But it's the same type of interval. And e is z sub c times the square root of sigma sub 1 squared over n sub 1 plus sigma sub 2 squared over n sub 2. Confidence interval is still between 0 and 1, and z sub c is still the critical value. In the summer of 1988, Yellowstone National Park had some major fires that destroyed large tracts of old timber near many famous trout streams. Fishermen were concerned about the long-term effects of the fires on those streams. However, biologists claimed that the new meadows that would spring up under dead trees would produce a lot more insects, which in turn would mean better fishing in the years ahead. Guide services registered with the park provided data about the daily catch for fishermen over many years. Ranger checks on the streams also provided data about the daily number of fish caught by fishermen. Yellowstone Today indicates that the biologists' claim is basically correct and that Yellowstone anglers are delighted by their average increased catch. Suppose you are a biologist studying fishing data from Yellowstone streams before and after the fire. Fishing reports include the number of trout caught per day per fisherman. A random sample of n sub 1 equals 167 reports from the period before the fire showed that the average catch was 5.2 trout per day. Assume that the standard deviation of daily catch per fisherman in this period was 1.9. Another random sample of 125 reports 5 years after the fire showed that the average catch per day was 6.8 trout. Assume that the standard deviation during this period was 2.3. For each sample, what is the population? Are the samples dependent or independent? Explain. Is it appropriate to use the normal distribution? And explain that too. The population for the first sample is the number of trout caught per day by fishermen before the fire. The population for the second sample is the number of trout caught per day after the fire. Both samples were random samples taken in their respective time periods. There was no effort to pair individual data values. Therefore, the samples can be thought of as independent samples. So even though we're doing a before and after, we're not specifically looking at one specific fisherman before and after the fire. It's random samples of fishermen. So it's not specific data values. It's not the same sample both times. It's a different sample each time. A normal distribution is appropriate for the et sub 1 minus et sub 2 distribution because sample sizes are sufficiently large and we know both the sigmas. Compute a 95% confidence interval for mu sub 1 minus mu sub 2, the difference of population means. Compute a 95% confidence interval for the difference of population means. So we have our data we stated before, and by the way, that should be et bar sub 1 and et bar sub 2, and we know that the critical value for 95% is 1.96. We can plug in the equation I gave earlier for E. So we plug those values in, and after we do the calculations, we get 0.5. The 95% confidence interval is same as usual, but with the ets bar sub 1 and ets bar sub 2 subtracting in there instead. We do that out, and we get that mu sub 1 minus mu sub 2 is between negative 2.1 and negative 1.1. What is the meaning in the confidence interval computed? We are 95% confident that the interval negative 2.1 to negative 1.1 fish per day is one of the intervals containing the population difference mu sub 1 minus mu sub 2, where mu sub 1 represents the population average daily catch before the fire, and mu sub 2 represents the population average daily catch after the fire. Put another way, since the confidence interval contains only negative values, we can be 95% sure that mu sub 1 minus mu sub 2 is less than 0. This means that we are 95% sure that mu sub 1 is less than mu sub 2. In words, we are 95% sure that the average catch before the fire was less than the average catch after the fire. So the biologists were correct that the fishing is better since the fire happened. Confidence intervals for mu sub 1 minus mu sub 2 when sigma sub 1 and sigma sub 2 are unknown. So the first section we just did was kind of a review of 7.1 with the subtraction added in. This is kind of a review of 7.2 with the subtraction added in. I wonder what the next one's going to be. When sigma sub 1 and sigma sub 2 are unknown, we turn to a student's t-distribution, just like we did in 7.2. As before, when we use a student's t-distribution, we require that our populations be normal or approximately normal, mound-shaped, and symmetric. That should say when the sample sizes are less than 30. We also replace sigma sub 1 by s sub 1 and sigma sub 2 by s sub 2, then we consider the approximate t-value attributed to Welch. Unfortunately, this approximation is not exactly a student's t-distribution. However, it will be a good approximation provided that we adjust the degrees of freedom by one of the following methods. So obtain two independent random samples from populations 1 and 2, where ets bar sub 1 and ets bar sub 2 are sample means from populations 1 and 2. S sub 1 and S sub 2 are sample standard deviations from populations 1 and 2. N sub 1 and N sub 2 are sample sizes from populations 1 and 2. If you can assume that both population distributions 1 and 2 are normal, or at least mound-shaped and symmetric, then any sample sizes n sub 1 and n sub 2 will work. If you cannot assume this, then use sample sizes n sub 1 is greater than or equal to 30 and n sub 2 is greater than or equal to 30, just like we were doing in the first section. Same confidence interval as the first section. E is the same as the first section, except it's now t sub c instead of z sub c, and all the rest of the stuff is the same as well. Except degrees of freedom is the smaller of n sub 1 minus 1 and n sub 2 minus 1. So you do minus 1 for both the n's, and then whichever is smaller is the degrees of freedom you take. Alexander Borbély is a professor at the Medical School of the University of Zurich, where he is director of the sleep laboratory. Dr. Borbély and his colleagues are experts on sleep, dreams, and sleep disorders. In his book, Secrets of Sleep, Dr. Borbély discusses brain waves, which are measured in hertz, the number of oscillations per second. Rapid brain waves, wakefulness, are in the range of 16 to 25 hertz. Slow brain waves, sleep, are in the range of 4 to 8 hertz. During normal sleep, a person goes through several cycles. Each cycle is about 90 minutes of brainwaves, from rapid to slow and back to rapid. During sleep, brainwaves are at their slowest. In his book, Professor Borbély comments that alcohol is a poor sleep aid. In one study, a number of subjects were given half a liter of red wine before they went to sleep. The subjects fell asleep quickly, but did not remain asleep the entire night. Toward morning, between 4 and 6 a.m., they tended to wake up and have trouble going back to sleep. Suppose that a random sample of 29 college students was randomly divided into two groups. The first group of n sub 1 equals 15 people was given half a liter of red wine before going to sleep. The second group of 14 people was given no alcohol before going to sleep. Everyone in both groups went to sleep at 11 p.m. The average brainwave activity 4 to 6 a.m. was determined for each individual in the groups. Assume the average brainwave distribution in each group is mound-shaped and symmetric. The results follow. Group 1, the et sub 1 values, with n sub 1 equals 15, we have this data. So it's the average brainwave activity in the hours of 4 to 6 a.m. So for group 1, we have a sample mean of 19.65 and a sample standard deviation of 1.86. For group 2, the average brainwave activity in the hours of 4 to 6 a.m. is below, and the sample mean is 6.59 and the sampled standard deviation is 1.91. Are the samples independent or dependent? Explain. Is it appropriate to use a student's t-distribution? Explain. Since the original a random sample of 29 students was randomly divided into two groups, it is reasonable to say that the samples are independent. A student's t-distribution is appropriate because both original distributions are mound-shaped and symmetric. We don't know population standard deviations, but we can compute S sub 1 and S sub 2. Compute a 90% confidence interval for mu sub 1 minus mu sub 2, the difference of population means. First, we find t sub 0.9, so the critical value at 90%. We approximate the degrees of freedom. As I said before, you take the smaller of the two n minus 1s. Since n sub 2 is smaller, the degrees of freedom will be 14 minus 1, which is 13. This gives us a critical value of 1.771. The margin of error is then 1.24 after you plug it into the formula. The C confidence interval, using formula from before, makes it so, well, I guess the mu's got cut off, but this should say mu sub 1 minus mu sub 2 is between 11.82 and 14.3. After further rounding, we have 11.8 hertz. So after further rounding, for some strange reason, the mu's are between 11.8 and 14.3 hertz. What is the meaning of the confidence interval? Mu sub 1 represents the population average brainwave activity for people who drank half a liter of wine before sleeping. Mu sub 2 represents the population average brainwave activity for people who took no alcohol before sleeping. Both periods of measurement are between 4 to 6 a.m. We are 90% confident that the interval between 11.8 and 14.3 Hz is one that contains the difference mu sub 1 minus mu sub 2. It would seem reasonable to conclude that the people who drank before sleeping might wake up in the early morning and have trouble going back to sleep. Since the confidence interval from 11.8 to 14.3 contains only positive values, we could express this by saying that we are 90% confident that mu sub 1 minus mu sub 2 is positive. This means that it's greater than 0, thus we are 90% confident that mu sub 1 is greater than mu sub 2. That is, average brain activity from 4 to 6 a.m. for the group drinking wine was more than average brainwave activity for the group not drinking. Estimating the difference of proportions, p sub 1 minus p sub 2. Like I said, this is a review of 7.3, but with the subtraction of the 2. We conclude this section with a discussion of confidence intervals for p sub 1 minus p sub 2, the difference of two proportions from binomial probability distributions. The main result on this topic is the following theorem. So we have two binomial experiments. Our n's are the number of trials, our r's are the number of successes. Our p hats are r over n's. Our q hats are 1 minus p's, and the p's are the population probability of success. Remember that p hat is the sample. The number of trials should be sufficiently large so that all four of the following inequalities are true. So n sub 1 times p hat sub 1, n sub 1 times q hat sub 1, n sub 2 times p hat sub 2, n sub 2 times q hat sub 2 all need to be greater than 5. The confidence interval is the same as before, but instead of the ETS bars, we have p hats. I just realized I don't know why they do the hat instead of the bar. It's kind of the same thing. They both mean samples, but I guess p's wear hats and ETS's have bars. Where e is the critical value times the sample standard deviation, so the critical value times the square root of p hat sub 1 times q hat sub 1 over n sub 1 plus p hat sub 2 times q hat sub 2 over n sub 2. C is still the confidence level, still between 0 and 1, and z sub c is still the critical value. In his book, Secrets of Sleep, Professor Borbély, this slideshow really wants me to say Borbély a lot, describes research on dreams in the sleep laboratory at the University of Zurich Medical School. During normal sleep, there is a phase known as REM, rapid eye movement. For most people, REM sleep occurs about every 90 minutes or so, and it is thought that dreams occur just before or during the REM phase. Using electronic equipment in the sleep laboratory, it is possible to detect the REM phase in a sleeping person. If a person is wakened immediately after the REM phase, he or she can usually describe a dream that has just taken place. Based on a study of over 650 people in the Zurich Sleep Laboratory, it was found that about 1/3 of all dream reports contain feelings of fear, anxiety, or aggression. There is a conjecture that if a person is in a good mood when going to sleep, the proportion of bad dreams might be reduced. Suppose that two groups of subjects were randomly chosen for a sleep study. In group 1, before going to sleep, the subject spent 1 hour watching a comedy movie. In this group, where there were a total of 175 dreams recorded, of which 49 were dreams with feelings of anxiety, fear, or aggression, so 49 successes. In group 2, the subjects did not watch a movie but simply went to sleep. In this group, there were a total of 180 dreams recorded, of which 63 were dreams with feelings of anxiety, fear, or aggression. So 63 successes in this case. Why could groups 1 and 2 be considered independent binomial distributions? Why do we have a large sample situation? Since the two groups were chosen randomly, it is reasonable to assume that neither group's responses would be related to the others. In both groups, each recorded dream could be thought of as a trial, with success being a dream with feelings of fear, anxiety, or aggression. P sub hat sub 1 is R over n, so 0.28, and Q hat sub 1 is 0.72. P hat sub 2 gives us 0.35, and Q hat sub 2 gives us 0.65. Since our four values are 49, 63, 126, and 127, they're all greater than 5. So, large sample theory is appropriate. What is P sub 1 minus P sub 2? Compute a 95% confidence interval for that. P sub 1 is the population proportion of successes, bad dreams, for all people who watch comedy movies before bed. Thus, P sub 1 can be thought of as the percentage of bad dreams for all people who are in a good mood when they went to bed. Likewise, P sub 2 is the percentage of bad dreams for the population of all people who just went to bed. The difference, P sub 1 minus P sub 2, is the population difference. To find a confidence interval for P sub 1 minus P sub 2, we need the values of Z sub C, sigma hat, and then E. From the table, we see that the critical value is 1.96. So, we get sigma sub hat by plugging in the equation we got before, which is about 0.0492. So E is 1.96 times 0.0492, which is about 0.096. So we plug that into the confidence interval, and we get that p sub 1 minus p sub 2 is between negative 0.166 and 0.026. What is the meaning of the confidence interval? We are 95% sure that the confidence interval between negative 16.6% and 2.6% is one that contains the percentage difference of bad dreams for group 1 and group 2. Since the interval is not all negative or all positive, we cannot say that p sub 1 minus p sub 2 is less than 0, or that it's greater than 0. Thus, at the 95% confidence level, we cannot conclude that p sub 1 is less than p sub 2, or that p sub 1 is greater than p sub 2. The comedy movies before bed helped some people reduce the percentage of bad dreams, but at the 95% confidence level, we cannot say that the population difference is reduced. So because we had some in the negative and some in the positive, we're not completely sure. So how to interpret that? Suppose we construct a C% confidence interval for mu sub 1 minus mu sub 2, or p sub 1 minus p sub 2. Then three cases arise. The C% confidence interval contains only negative values. In this case, we conclude that mu sub 1 minus mu sub 2 is less than 0, or the same for the p's. And we are therefore C% confident that the first mean is less than the second mean, or first probability is less than the second probability. Number 2, the C% confidence interval contains only positive values. In this case, the difference is greater than 0, and we can be C% confident that the first mean or proportion is greater than the second. The C% confidence interval contains both positive and negative values. In this case, we cannot, at the C% confidence level, conclude that either the first or the second is larger. However, if we reduce the confidence level to a smaller value, possibly 90% or 80%, then the confidence interval will, in general, be shorter. Another approach, when possible, is to increase the sample sizes. This would also tend to make the confidence interval shorter. A shorter confidence interval might put us back into case 1 or case 2 above. And last thing I'm not going to talk too much about, but how to find the confidence interval for mu sub 1 minus mu sub 2 when the standard deviations are the same. So we consider two independent random samples, x bar sub 1 and x bar sub 2 are sample means from populations 1 and 2. S sub 1 and S sub 2 are standard deviations, and N sub 1 and N sub 2 are sample sizes. If you can assume both population distributions 1 and 2 are normal, or at least mound shape and symmetric, then any sample sizes will work. If you cannot assume this, then use sample sizes where they're both greater than or equal to 30. So the confidence interval stays the same, where E is T sub C times S times the square root of 1 over N sub 1 plus 1 over N sub 2. S is the pooled standard deviation, so this formula. C, once again, is the confidence level, where C is between 0 and 1, and T sub C is the critical value. And the degrees of freedom are N sub 1 plus N sub 2 minus 2. Now time for the sponge. Consider two independent normal distributions. A random sample of size n sub 1 equals 20 from the first distribution showed x bar sub 1 equals 12, and a random sample of n sub 2 equals 25 from the first distribution showed x bar sub 2 equals 14. Given sigma sub 1 is 3 and sigma sub 2 is 4, find a 90% confidence interval for mu sub 1 minus mu sub 2. And for part B, suppose sigma sub 1 and sigma sub 2 are unknown, but from the random samples you know S sub 1 is 3 and S sub 2 is 4. Find a 90% confidence interval for mu sub 1 minus mu sub 2. Consider two independent binomial experiments. In the first one, 40 trials had 15 successes. In the second one, 60 trials had 6 successes. Find a 95% interval for p sub 1 minus p sub 2. Alright, that's it for the lesson. Once again, please make sure to take notes on everything. Take a picture of everything, submit it to Doodle Classroom, and have a good night.